Hey, hello everyone. In this video right now, I'm not really going to showcase much content, so this should be a quick video. What I'm going to talk about is the fact that I've not been able to make much progress in the bone and animated level part stuff side of the code because I've been focusing mostly on solving small issues that the exporter had before I could actually get started implementing that side of the code. And I wanted to make a small report where I talked about some of the most major things that I've made, which, for example, as you may have seen in the previous video, I did fix a problem with the lightning, where the orientation was not properly being calculated. And in this video I want to talk about one of the most important things, which is the fact that if we go over to our code right here, we can see that I have made some modifications. So there's a lot of comments because I'm not really too familiar with Python, so there's a lot of things that I had to note for the future in case I forgot anything about this project. But anyway, the thing I was looking for to showcase is the fact that we no longer perform transformations on every single point whenever we export the mesh, because this scene right here that I was showing you would take something like 10 seconds to export before, and having multiple trees in the scene would actually bump up the export time to about, like, in total over a minute worth of export time, right? And a problem we had, which I have documented in some pictures right here, I think, yes, you can see that the export time we used to have was pretty absurd. At first I made a debug print that only documented the export time that it took to perform the whole object creation part and then the total time, right? So you can see that for creating all of the objects in the scene and writing them in a data structure that can be useful for the JSON generation, right? This is where we actually translate all of the information to a format that Magicka can use in memory in Python, right? It took over 36 seconds, and that's a pretty big amount of time. And since the total is 52 seconds, that means that we had over 10 seconds worth of time invested into writing the JSON text into a file. And that is absurd. It is insanely slow, right? So obviously Python is not a very fast language, and there's a lot of problems with it where code that you would usually write in any other language and it would be normal because it would compile to a very simple set of instructions, in Python actually is a bunch of instructions that have to be interpreted, and that's very slow. So a lot of for loops have been changed with small, like, list comprehension stuff and whatever, but that wasn't even the major point. The major pain point that we had was completely different, and it was the fact that we were calculating the transform matrices for the y app of the scene, right? Like, we were translating every single object by picking their transform matrix, and then we would translate it to a y app coordinate system, which is what Magicka uses, right? And this has a problem because it needs to go through a bunch of function calls, and the operation itself is not that slow, but it is the function calls that have a lot of overhead in Python, right? And then we would use a function. I had a set of translate point, translate whatever, right? So if we go to translate, we have a bunch of functions to translate points, matrices, vectors, and get, well, this masked one returns tuple field with translation matrix, rotation matrix, scale matrix, etc., right? And the problem with this stuff is that even if the operations themselves should be extremely fast to be performed in a modern computer, and probably even in an old computer, they would take a long time in Python, especially because of the whole function and the fact that we would be calling this for every single object, which shouldn't be much of a big overhead, because what is the difference between doing that versus getting its own matrix, right? But we'll talk about that in a while. So if we go over to our def generate mesh function, for example, the other one, we can get a lot of insight into what the problem is. So at first we would get the transform, and rather than using this function, which what it does under the hood is actually make an if statement and just return either matrix world or matrix local to get the coordinates in global and local. And the fact that we have this thing right here is for the bone implementation. Actually, this is for the animated level part because they have coordinates in relative coordinates to their parent. So that's going to be a pain in the ass to implement with the old system. So that's part of the reason why I didn't make that much progress this last few days, because I've been reworking a lot of the code, right? And before we would just get this transform matrix, like get matrix world and then translate it with the y up and y inverse matrices, right? And we would do that for every single object. This is done for every single object of type mesh. And then in here we would perform every transform with a function called to the translate point, translate vector, right? And you should think that it would be the exact same thing as what we're doing right now, but it's not, even though it's the same code inside of it, because the function call itself has already quite a big overhead and passing the parameters and copying them around as well. So only removing the function calls already shaved off like in total 20 seconds or so from the whole export process, right? And at the end of it all, I realized quickly that if we just use the transform directly, because these math utils functions are actually implemented under the hood, so it's not just pure Python in here, so these are as fast as they can get, right? These matrix multiplications. So it was better to just pre-calculate the transform. I was like, okay, how do I pre-calculate the transform? And this is where the problem began. Like, the whole idea of calculating the transform here was allowing people to have in Blender their scene like this without modifying everything, because then you would be forced to pick your scene root and rotate everything around the x-axis and export everything like this to have it in the same coordinate as Magicka, right? We could do this like in 3ds Max. Well, actually it's probably crashed because I've kept it open for a long time, but it's loading. Give me a sec. So if we bring it over to this other screen, we can see that the root of the level, probably if we can pick it up, if we go to rotation, you can see that it's got 90-degree rotation, right? Everything within it is going to have that 90-degree rotation when we export it. Sadly, Blender is not exactly the same way, because if we go ahead and create a new object, let's just save this map as it is and make a new map so that you can see the problem. Well, map Blender file, right? So if we create an empty, for example, with plain axis, which would be our origin point, it has no rotation right now, and we assign it a 90-degree rotation. We go ahead and have a mesh right here, and we put it inside of this object right here. This object right now, if you fetch its matrix world, it actually has a 0, 0, 0 rotation as promised in here, right? So why? Because we attached it after we performed this rotation. So the order of the transformations is applied first this one, then we apply all of the transformations of this object. So if you want to have everything be rotated by its parent, you have to have the parent with rotation 0, then attach the child, and then rotate the parent. And then this object, even though you see 0, 0, 0 in here, internally actually has a transformation matrix from its parent that does contain the 90-degree rotation, right? And this would be correctly translated. So if you wanted to create any other objects for Magicka's coordinate system without having to unrotate this, add the object and go back to it, right? Because imagine we did this now. We could just work in our C app coordinate system and we wouldn't care about any of that, right? It would properly get translated with the old system. But we would have a problem, which is that if I wanted to add another mesh, now this other mesh right here that I put in here is not going to have the coordinate system that is the correct one. And I can prove it like this. If we move it up and down, you can see that we're moving it along the C-axis. But we pick this one up and we move it up and down, even though I'm selecting the global C-axis, you can see that the axis that it's moving within its parent is the y-axis, right? So this one is correctly translated to a y-up system, this one is not, and this one would not export correctly, right? So that's a problem with how Blender's coordinate system works in respect to 3ds Max, and why it was far easier to the people who made Magicka to just ignore this problem completely and just make the root be rotated 90 degrees and then work inside of that root freely, right? For us, we don't have that freedom because we either put every single object as a default cube or whatever, bunch of default lights, and then we rotate everything and only work on copies of these objects, because any object copied from another that was already translated is properly translated, or we work correctly and then we rotate everything by hand. Okay, so that's a problem. And what was the solution? Well, very simple. Since this is much cheaper, right, the reason why we want to do all of this, okay, we can go back to the code, is that this transform matrix, right, if we go to Blender and perform any transformation here, right, you can see it's instantaneous. Even though the Python code performing absolutely any matrix multiplication is gonna take ages, you can see literally every single frame I'm performing a bunch of matrix multiplications, because as I'm moving this thing right here, I'm changing values of a rotation matrix. But apart from that, whenever the object is rendered, it has a set of values for its rotation, location, and scale, and then it has to multiply them together in a specific order to get the correct transform matrix, and then pass that to the graphics card, right? So it's doing a lot of work, an insane amount of work, if you think about how slow Python is, even though that the truth is, this whole work where it's multiplying multiple matrices to get the real transform matrix is actually a super small amount of work. Even though for a human, multiplying a matrix should be something massive, especially like 3 or 4 4x4 matrices for a single object, then imagine thousands of objects in a scene. For a computer, that's so small. It should be extremely fast to do. Otherwise, there wouldn't have been 3D games out there or any graphics programming before the year 2020, right? So obviously, this is a very fast to perform operation, even on low-end hardware. Like, computers are insanely fast. The problem is how slow Python is, with all of the layers of abstraction or overhead, right? So the idea was to take advantage of the fact that these transformations are already here. They have been performed at the C code level, because I'm using Blender's interface, and everything you see in here has been programmed in C, right? Only the add-ons, which are extra things like extra properties or exporters and importers and stuff like that, are programmed with Blender's Python API, because that's what is extensible about Python. So the basic functionality is in C. And I thought, well, then why don't we perform automatically from the Python code one single rotation of the root of the scene, right? And this single rotation that we're going to apply is going to be bringing us to the y-up coordinate system, and then we can just undo the rotation afterwards. So we have our whole code to get the scene roots, the animation root, etc. None of that matters. What matters is that we perform a rotation, and then we get the data from the scene, and our transform is already applied. We don't have to calculate any other transform matrices, because Blender has done that work for us. And then we undo the rotation to go back to what we had before, right? And obviously we need to use this thing right here. Well, obviously, quote unquote, documentation doesn't really talk about this. I had to look it up online because this was not working, but doing it by hand was working. So it's clear if you return a cancel operation here before getting the scene data, that the rotation is applied after the program freezes. And it freezes the moment you enter the export operator, which is way up here, right? So whenever we enter the export data, we basically freeze the whole program until this operator has finished, right? There's like no concurrency in there, right? So for that to work properly, we have to send a signal that is, hey, Blender, update the data. I want you to rotate this. But before we actually go and do any functionality where we go object.data to get the information from the object, or object.matrixWorld or matrixLocal or whatever, I want you to actually update this data so that when I fetch the objects actually contain their proper updated values, right? So that's what this whole update thing is about. And in total, I think it adds like 0 point something seconds of overhead, which is kind of sad, but we're gonna look at the export times now. So I've got a bunch of photos here, and I want to show you this other one right here. This was after performing a few optimizations of the first one that I talked about, which you can see that the total time was still 49 seconds, right? I added more debug stuff, and this is how I realized by slowly profiling my code where the overhead was, which is at the mesh generating mostly, right? This is where the overhead mostly was. Getting the data, like this thing right here, where we iterate the entire scene hierarchy to get all of the objects and add them to arrays, 0.00009 seconds. Like, this is absurdly fast. This is extremely fast, right? And this operation should also be fast, but the whole overhead with performing those matrix operations from Python was slowing us down. So this is the result after doing everything. If we go over to Blender and open this map, right? So let me first show you the last picture, which we have somewhere around here. Nope, this picture is old. Let me just go ahead and demonstrate to you then. We can go ahead and export this object and press untitled, right? And now remember, our export time was 50 something seconds, about a minute, right? And we're going to export the object. It's done, it finished, it's already over. This is the new export time. Look at that. Data generation 0.5 seconds, right? All of this right here, in total it took less than 1 second, and this is because OBS is open, right? When it was closed, it was taking 0.6 something seconds. Now it's taking 0.7 something seconds because I have a lot of things open, and that's adding a small amount of overhead. So think about how fast this is now, right? So if we go ahead and make a test, for example, adding tons of trees. These trees are pretty high poly for Magicka's data format, because in XNA games it's not really common to have such high poly objects. This should slow down the export process. This would have taken like over a minute and a half in the exporter, right? Let's just export this now. And if we export it, it's gonna take a while. This is gonna take a few seconds probably. And let's just imagine that if it's about less than 1 second for every single tree, then whoops, it already finished. When it minimizes like that is because it has a problem with the graphics interface, but it finishes. And here we go. It took 8.4 seconds to export this scene. So this might seem slow, but if you consider the fact that every single tree has in total like 15k vertices, then that's a pretty nice time, right? Like that's a pretty nice time, especially when it's actually iterating every single vertex and every single face and duplicating this information to allow whenever it has to be duplicated, because it's going through a dictionary and making a lot of checks to make sure that the UVs of the mesh can be translated from a Blender's face-based UV to a regular vertex buffer where we have vertex-based UVs. So we have to duplicate data if we want to preserve the correct face-based UVs that an artist would work with usually, right, in any 3D software. So this right here is actually quite insane. It's pretty cool. It's pretty cool because in total our scene before triangulation has like 542k triangles, right? But if we were to go ahead and triangulate this tree right here, right, let's open it and triangulate it. This thing right here in total, well, I mean, sorry, we were looking at triangles. This is already triangulated. My bad. My bad. This means that we actually don't have any extra problems. Yeah, it's already triangulated. I was thinking that we could maybe get a higher value, but yeah, we have like this many faces, this many triangles after it's triangulated. I misread this one thing. So yeah, we have in total like 30k triangles in this tree. That's pretty insane. right? 30k triangles. And in total, we got over 500,000 triangles in this thing, which is not that big of a deal. But when you're writing this to a JSON format, like you're translating this to text, this is a pretty big improvement with the time we had before. So yeah, I'm pretty happy with that. Pretty happy. And of course, the number of triangles here is going to be smaller than the one in Magicka, but yeah. Anyways, let's just open them up again, right? And this is our level as it is right now. And we can go ahead and look at it in Magicka, right? So I'm gonna open the game, load the map, and there's nothing new to show. I just wanted to show you that after we export and compile the map, it still looks just the same as it did before. The nav meshes and the collisions work okay. So this change is very beneficial. It has really sped up the export time by fixing a lot of small problems and oversights. So it's really good. It's really nice. There's really not much else to showcase other than technical stuff, but yeah. If we go ahead and try to use the trigger, it's also properly, translated still, and the lights as well, like everything works, even the water itself, right? So we've just made the whole development process a whole lot easier, and also the whole export and user end of the program also a lot easier, because we've just shaved off a lot of waiting time for map export and compilation pretty much. Oh, and also I forgot, remember how I mentioned before that there's like 10 seconds of overhead on the JSON writing side of the code, right? Those are for a bunch of reasons. The JSON writing in Python is extremely slow. It's really slow. So the function JSON.dump, which basically is the default JSON, we could use any other library. I don't want to write my own, and I don't want to use any of the other libraries because I want this add-on to work out of the box. So it's only going to use the default things that come with Python and the default things that come with Blender's Python API, so that anyone who installs Blender can just run this without installing anything else, right? And as you can see, this was the old dump function, and this is the new one we have now. We, rather than dumping into the file, what we do is dump into string, which is way faster, and then writing the string itself. It's kind of slow still, but it's way faster than dumping a JSON file, because JSON.dump actually goes in extremely small segments, like making tons of write operations under the hood, right? Like inside of this, there's tons of file.write. They are not buffered the same way that they would be by default in C, which is kind of weird actually, because C, like even default buffering, which is not great, is far better than the buffering offered by dump, but I don't know why. But yeah, so writing to the string is way faster, and then writing the entire string to the file is way faster. And we could even modify this probably to have better buffering, but we don't care about that anyway, or maybe use a memory map file or whatever. The indentation, we don't care about this. The generated files are ugly now. That's the only downside, right? Like they don't have any formatting, which sucks, but they don't have to have formatting. I mean, you can still edit them by hand. You just need to look at the stuff better, I guess. It's gonna take a while actually to search through that with Control F. But yeah, it's easier to parse for text editors as well, because there are less lines to buffer. And it's easier to export because there's no overhead anymore, so this speeds up things quite a lot. And it's kind of sad, to be honest, because I know how I would program this in C with absolutely zero overhead with indentation, but I don't know why the JSON.dump functionality doesn't really properly implement that in Python. I guess that they wanted a generic implementation. So yeah, the separators, they don't have a new line separator because I don't need new lines after I change indent to be none at all. And check circular is actually an option that makes the JSON parsing, generation in Python, right? Check if the structure you generated is circular to stop generating at some point when it finds something that it already generated before, to prevent circular dependencies where it would be infinitely writing files until it crashed or ran out of stack space or whatever, right? Like when it got too deep on the recursion, it would just stop working, right? So we don't need that because our structures are not circular, and even the bones and recursive structures like binary trees, they actually work either by having two children which are unique, or they have a system which I wrote by hand on the Magicka Map tool, which is that they use indices as reference, right? So we reference objects through an index, which pretty much makes it impossible to have these recursive structures, because we have a list with every single object, and whenever there's like a child object, rather than copying the whole data, which was a bug we had and we fixed in a previous video, by the way, rather than doing it like that, we just contain an index and say, hey, I'm pointing to this object right here, copy it from here, a list that you actually loaded in memory before. And that's why we don't need to check for circular, because we don't really have it. So yeah, the thing is that I'm going to add this as an option because people might want to generate files that look pretty. So I will probably say pretty printing or something as an option in the files. Yeah, that's the only thing I'm going to add to the end of this video. And yeah, I think this is pretty much all there is for me to comment. In short, a massive speed up by fixing a bunch of oversights and changing just a tiny bit the way that the code is designed to work better with the model that exists in Python. So we've gone from taking a long time to basically having instantaneous exports, which it can get a bit slow when you have high poly scenes, but Magicka's format itself is not even thought for high poly meshes, right? So of course it's going to be slow to translate this stuff. But what I'm trying to say is that even though I didn't make progress in the area that I wanted, I've made progress in tons of areas that are going to help me progress further in that direction. And hopefully from this point onwards, the exporter does nothing but get faster, right? Like I hopefully find more and more optimizations that we can perform to actually make things better. That would be pretty cool, to be honest. And yeah, there's nothing else for me to comment in this video. See you in the next one.